All right, gang, stat 1150. I guess the title would probably help you could see that. The title of this is When Confidence Intervals in Hypothesis Testing Don't Agree. So let's look at an example. Let's say that we would like to test the claim that mu is equal to 10 versus h sub a mu greater than or equal to 10. And let's say we're testing at 0.05. And to test this, we want to collect some data. So let's say that we collect 5 measurements. And let's assume normality, independence, and randomness. All right. So the measurements that we collect are 8.7, 13.2, 40.1, 33.7, and 38.2. So the very first thing I want to do is I want to calculate a test of hypothesis on h sub o. And then I want to do a confidence interval. So 0.05, we're going to do a 95% confidence interval. And let's see what happens with these. So I'm going to go to StatCrunch. First thing I'm going to do is I'm going to type in the numbers. Probably already should have had this done, but I didn't. So 8.7, 13.2, 40.1, 33.7, and 38.2. Don't you love small data sets? All right. So I'm going to hit Stat. I'm going to calculate conduct the test of hypothesis first. I'm going to use the easiest one. I'm going to use the p-value approach. So one sample with data. So I'm going to mu equal 10 and mu greater than 10. All right, compute. So I've got a test statistic of 2.55 and a p-value of 0.032. So the p-value 0.032 is less than our alpha of 0.05. So we reject h sub o. There's more evidence to conclude that the mean is greater than 10 than there is to conclude that the mean is equal to 10. So from the hypothesis testing, all the evidence is in support of h sub a. All right. Now, let's go to the confidence interval. So I'm going to conduct a confidence interval on t-stat, one sample with data. Confidence level 0.95, choose variable 1, and compute. Well, confidence interval runs from 8.50 to 45.06. Notice what we're testing, 10, is contained in our interval, so the confidence interval result supports that the mu is equal to 10. So we have a contradiction here, don't we? Now, I want to show you this because this is something that happens, and it only happens in one situation. When we're conducting a greater than 10, we're conducting a one-tailed test, greater than or less than. In our distribution of sample means, now, first of all, if we're doing the confidence interval and we're looking at the value that separates the middle 95%. So we can go to StatCrunch and go to calculator and find the two values that encompass the middle 95% for degrees of freedom 4. That's 0.95. That's going to be between negative 2.78 and positive 2.78. So the values between there and there, this is going to be where our confidence, the means that are going to fall in our confidence interval. But if we're doing a test of hypothesis and we put all of our rejection region out to the right, of 5%, 0.05, this value right here so 0.05 to the right, we get 2.13 as our cutoff. So guys, a test statistic, any data that has a test statistic of 2.13 or higher is going to reject. However, the test statistics between 2.13 and 2.78 are going to be in our rejection region, but they're also going to fall in our 95% confidence interval. So will we get contradiction? Now guys, I haven't calculated the test statistic, or at least I didn't write it down, but I'll guarantee you it's between 2.13 and 2.78. Let's just go ahead and run that. Well, we did run it. We did it for the hypothesis test, right? So it's 2.54. So our test statistic is right in here at 2.54, which contradicts. Now, how do you take care of that? One way you can take care of it is you will never, ever, ever, ever get this result if you calculate your hypothesis test for a not equal to. If you use a not equal to alternative hypothesis, your confidence interval and your hypothesis test will always coincide. If you use a one-tail test, then you have to multiply this by 2 and subtract by 1 to calculate, subtract from 1 to calculate the confidence level that you need for your confidence interval. So the 0.05 multiplied by 2, 0.10. 1 minus 0.10 is 0.9. So you would need to calculate a 90% confidence interval to get the interval in the hypothesis test to agree. Now, hope that didn't go over your head. Let's go ahead and just calculate it out. So if we do a t-stat, one sample with data, and we do a confidence level of 0.90 instead, then we're going to get in a situation where 10 is not going to be included, which it shouldn't be if you rejected the claim of 10. So most people don't like this kind of wackiness here of multiplying the alpha by 2 and subtracting by 1, and they just always test the alternative of not equal to. And if they want to know whether or not the mean is higher or lower, they just calculate a 95% confidence interval, and if that entire interval is above the claim, then they conclude it's greater. If that whole interval is below the claim, then they conclude that it's less than. So that takes all the wackiness of the hypothesis test and the confidence interval not agreeing. It completely takes it out of the equation. So how would that work with our problem? Change h sub o mu equal 10, h sub a mu greater than or equal to 10, to h sub o mu equal 10, h sub a, mu not equal 10. So let's calculate it. Stat, t-stat, one sample with data. Select the variable, do 10, not equal to 10. What do we get? We get a p-value of 0.063. Fail to reject. So when we calculate our confidence interval, which we did earlier, then 10 is going to be contained in our interval, which we saw it did. Okay? So, and if our p-value had been less than 0.05, then 10 wouldn't have been in our interval, so our whole interval would have either been above 10 or below 10, and if the entire interval was above 10, we can conclude, statistically speaking, that mu is bigger than 10. If the entire interval is below 10, then we can conclude, statistically speaking, that mu is less than 10. So, guys, that's all I got. Take care.